chapter 2, what we want to do is we want to be able to look at some different types of functions, and we'll be doing quite a bit of this throughout the course of this particular course. To begin with, what we're going to look at is we're going to look at something that we call variation functions or variation equations. And to start out with here in section 2.1, we're going to start with the most basic one, and that's just direct variation. When we talk about direct variation, basically what we're saying is we're talking about an equation in which one variable is a multiple of another variable, or the product of variables. In other words, that variable times itself. Okay? Well, sometimes it's just easier to think about that and look at that in terms of a function. So really, when we're talking about a direct variation function, functions now have independent and dependent variables. Basically, we're saying, hey, it's got to be of a form that looks something like this, written in an equation form, where y is our dependent variable and x is our independent variable. We'll say that k is a constant of variation. Okay? Well, k cannot be equal to 0, and we also know that our n, or that exponent value, has to be greater than 0. It needs to be an integer as well. Well, it doesn't need to be an integer, but for the most part, we're gonna work with it from the standpoint of an integer. Okay? So in words, we would say y varies directly as x to the n, or y is directly proportional to x to the n. One of the things that you'll have to be able to do in this chapter is be able to write things in words and equations and go back and forth between those two. Okay? An example of a variation equation is one that you've used quite a bit thinking back to your geometry time, and that is a equals pi r squared. We know that's the area of a circle is equal to pi times the radius of that circle squared. Now, this is an example of a direct variation equation. Now, let's think about the parts of it. K, the constant of variation, would be pi. N, the exponent there, is 2. And our independent and dependent variables of r and a, where r being the radius and a being the area. So there's an example, the most basic, a very, very basic example of a direct variation equation. Alright, so let's take a look at this first example. It says the surface area S of a cube is directly proportional to the square of the length E of an edge. First thing we want to do is identify the dependent and independent variables. So if I'm looking at the situation, I can say that the surface area is dependent upon the length edge. Therefore, I would say S is my dependent variable and E is my independent variable. Part B says a cube with length of 5 centimeters and a surface area of 150 square centimeters determine the constant of variation. So what we now know is we know an ordered pair that satisfies our variation equation. What we need to do though is we need to figure out what is that constant of variation. So what we're going to do is we're going to substitute 5 in for E, and we're going to substitute 150 in for S after we write a general formula involving those two. So this would be a general formula based on the information from what we're given, that S is directly proportional to the square of the length of the edge. So I wrote that. Now what I want to do is I want to plug in the 5 and the 150. Once I do that, once I've plugged those in, now what I want to do is solve for k. So I'm going to divide both sides by 5 squared. And once I do that, I have 150 divided by 25, which is equal to 6. Therefore, k would be equal to 6. Now, the third part says, all right, now let's rewrite the equation with our independent with our constant of variation in there. So I'm going to rewrite this now as S is equal to 6e squared. Notice how I didn't have the 150 and the 5 in there. I only used those to help me figure out what k is. Okay. Now I have a formula that I can use to find any value of s if I know e, or for that matter any value of e if I know s. So the last part here now says, well, what is the surface area of the cube if the edge length is 8 centimeters? Well, now all I'm going to do is I'm going to say, well, s is equal to 6 times 8 squared, which is equal to 384. So this would be the value of that surface area then in, and we'd want to include our units here because the surface area would be 384 centimeters squared. So that would be our answer for that particular example. Alright, the different parts of that last example really are kind of the main pieces of what we would do if we were going to take any variation problem. And this is kind of the procedure that you want to use if you have a variation problem to solve. You begin by writing the general variation formula. Then you're going to be given enough information about the two variables, the independent and dependent variable, to solve for k, just like we did in the example. And then you're going to want to take that k value and plug it back into that general formula. That will give you a specific formula for that situation. Okay, and a lot of times we'll ask you for that specific formula. And then finally, once you do that, the last step would be to use that formula to find whatever answer you're looking for. So this procedure is going to be really important. You're going to use this quite a bit within this chapter. So let's take a look at the second example now. And then in the second example, what we're going to try and do is we're going to try and apply these 4 steps. So at this point, I'll go through the example, but you may want to, just to kind of test where you're at with this, you might want to just pause the video and try and do it yourself first, and then watch the video and make sure that you have it correct. So to begin with, we're going to write the general variation equation. Well, it says that m varies directly as the 5th power of p. So I'm going to say that m is equal to k, the constant of variation, times p to the 5th power. Okay. Step 2 now, it says, now what's k if m is 96 and p is 2? So I'm going to plug 96 is equal to k times 2 to the 5th power. Well, I know that 2 to the 5th power is 32, so I could say 96 is equal to 32k, and then I can divide by 32 on both sides. And that would mean that k would be equal to 3. So we've figured out what k is, so now we're going to come to that point where we're going to rewrite the equation with k in it. So let's do that at this point. I've got some marks here I'm going to erase. If I rewrite that with k, my new k value in there, I'm going to say m, not 96, m is equal to 3p to the 5th power. And then finally, we want to do the last step, which is solve for whatever we're looking for. In this case, we're solving for when p is equal to 5. So I'm going to say m is equal to 3 times 5, not p, excuse me, 3 times 5 to the 5th power. Now if we do that on our calculator, I believe that would come to 9375. Okay? Therefore, the value of m when p is equal to 5 would be 9375.